Hi everyone, my name is Ariel Farrell, and for this project I decided to further explore L'Hopital's rule. Now if you're unfamiliar with L'Hopital's rule, this is a method used to find limits of functions. Many times we are given functions in which we can't just use inspection, factoring, and other methods to find the limit. In this case, we can sometimes turn to L'Hopital's rule. Now the reason I say sometimes is because this method can only be used if the function has a specific ratio or form. Now my question is, why does a function need to have a 0 over 0 or an infinity over infinity form in order for the L'Hopital's rule to apply? L'Hopital's rule was first introduced to me in my Calc 1 class, and I found that it was useful in my other continuing calculus classes. And in these calculus classes, I was simply just taught to check the function's form that I was given, and if that form happened to be 0 over 0 or infinity over infinity, then I can continue on and take the numerator and denominator's derivatives. Ever since I was introduced to L'Hopital's rule, I just always wondered why the ratio was so important. Now the mathematics involved in order to use L'Hopital's rule are usually just simple derivative computations. So L'Hopital's rule can be used as long as the function you are given has the form 0 over 0 or infinity over infinity. So if the function has either of the forms 0 over 0 or infinity over infinity, then the limit as x approaches c, f of x over g of x is equivalent to limit as x approaches c, f prime of x over g prime of x. For example, we are asked to find the limit as x approaches 1 of x cubed plus x squared minus 2x all over x minus 1. Now for this problem, you may be looking into factoring. However, we can actually apply L'Hopital's rule. Now the very first step in checking if you can even use L'Hopital's rule is checking for the ratio. To check the ratio of the function, all you have to do is plug in what x is set to go to into the original functions. If you happen to get 0 over 0 or infinity over infinity, then L'Hopital's rule may be used. So once you have checked that L'Hopital can be used for the function, you can then set the numerator to f of x and the denominator to g of x. You will then find the derivatives of the numerator and the denominators separately. Now for this specific function, we only had to use L'Hopital's rule once to get it to where we wanted it to be. A condition that would tell us that we need to further use L'Hopital's rule is if we still continue to see a 0 over 0 or infinity form. However, for this specific function, we can see that all we have to do now is plug in the number 1 for all the x's that we see in the function. And once we do that, we can see that the limit of this original function is equal to 3. So here I have the same function that we just worked on not too long ago on GeoGebra. So x cubed plus x squared minus 2x all over x minus 1, which is a parabola. Now the problem stated that we wanted to find the limit as x approaches 1. Now with this, we can see that it does in fact equal 3. However, if we did not have this graphing utility, we would then use L'Hopital's rule to get the function 3x squared plus 2x minus 2. With this, we can also see that this parabola, although it is a totally different parabola, the limit still in fact equals 3. So for a second example, I decided to choose the function 4x cubed minus 6x squared minus 1 all over 2x cubed minus 10x plus 3. I decided to see the limit as x approaches infinity. I had already checked that L'Hopital does apply, and I received the form infinity over infinity after I plugged in infinity into the x's. Now we can see, just by inspection, that the limit appears to equal 2. Now you may already be thinking that the answer is 2 just by inspection because the degrees are the same and all we have to do is take the coefficients. However, another route that we can take is by doing L'Hopital's rule. Now the second function that I have typed in is what I got after doing L'Hopital's rule once. By looking at the graph, we can see that this limit is as well 2. It will never go above 2. Now because the second function still has the form infinity over infinity, we can then compute L'Hopital's rule once again. After doing this, we can see that same thing, the limit is still 2. Now with this third function that we found, we can still take L'Hopital another step forward. We will then get 24 over 12, which then simplifies to 2, which is what we got in the very beginning. So for my final example, I have chosen a function that actually does not apply to L'Hopital's rule if we let x go to 3. If we let x go to 3, we will not get 0 over 0 or infinity over infinity. For demonstration purposes, I am going to act as if L'Hopital's rule does apply to this function. If we take the derivative of this function, we will get 1/2. As x approaches 3, it appears to be that the limit actually equals 1 and not 1/2. With this visual aid, we are able to see that we performed L'Hopital's rule when it was not supposed to be used. With this previous example, we were not allowed to use L'Hopital's rule because the form that we got was not 0 over 0 or infinity over infinity. The reason that we can only use L'Hopital's rule for functions with the form 0 over 0 or infinity over infinity is because we have to make sure that the functions that we are creating have the same end behavior. I would have to say that the hardest part about making this project was creating the functions that I wanted to use. I knew from the very beginning that I wanted to have one function that had the form 0 over 0 and another function that had the form infinity over infinity. This project made me realize how difficult it might be for teachers to even come up with the questions that they want to use. As students, we always find how it's super hard to solve the problems, but we never really think about how difficult it may be to actually create the tests that we want and to create the homework problems that we want to use. In general, I believe that when you teach something, you should always know the backstory, the proofing, and why everything is the way it is. By providing students with more information on why things are the way they are, it allows them to better understand the concepts that you're teaching them. So in this specific case, we should be teaching students that L'Hopital's rule isn't just finding the form and taking the derivative. We need to teach that although we are creating totally different functions, these functions do have the same end behavior, which makes their limits equal. Providing our students with the most information that we can on math concepts, I believe that it'll bring up more critical thinking and students won't be afraid of asking the question why.